Thank you.
So tomorrow is same time.
Same time is fine, right? You will be here.
I'll be here. So tomorrow I have a class at 9:30 to 11. So if you start at 11:30, 11:30.
Yeah. Okay, before I start, I just want to say that tomorrow also I will take class. I'll take from 11:30 to 1:30. Fine? Is it fine with all of you? Can you hear me? Are you people able to hear me?
Yes, ma'am.
Yes, ma'am.
Okay, so tomorrow's class is from 11:30 to 1:30, 2 hours. All right? Okay.
Ma'am, can you switch off the lights?
Okay. Which one? Let's see. One second. This light is fine.
And the
No,
light
ma'am.
just above the black.
On the
The blackboard light. Okay. Is it fine now? Is
Yes,
it
ma'am.
So let's summarize what we have done so far. So what I have shown you, or what we have done so far, is definition of Cartesian tensors. So we talked about the definition of tensors, and yesterday I also introduced objects which are pseudo tensors. And in this process, we also studied about what we mean by rotation transformations. So that was an incidental kind of study. So we studied about rotations and rotation transformations and in general. So what is the form of a most general rotation transformation? And of course, I've restricted all my studies to 3-dimensional space, but it's easy to extend it to n-dimensional Euclidean space. And then after that, we did a little bit of tensor algebra. That means we talked about adding tensors, subtracting tensors, and then we talked about product or multiplying tensors, combining that means. Then I didn't do this part, which is essentially taking off division, but I'll do this through an example because I thought that might be more easy. Okay. So we did a little bit of tensor algebra, adding, subtracting, multiplying, and quotienting of tensors. Okay. Then what did we do? Then I introduced in particular isotropic tensors, some specific isotropic tensors. And in particular, we looked at these two tensors or these two objects, delta ij and epsilon ijk. And then using that, of course, we can say that how to combine more generally or more general isotropic tensors. So this is something. Then what did I do? Then I introduced the idea of tensor fields. Right? Then we talked about generalizing some integral theorems or generalization of Green's theorem and Stokes theorem. Okay. For tensors. Alright. So essentially, this is what we have done so far. That and as a prelude to this, what I did was a little bit of vector spaces, very little, but so for vector spaces, given vector spaces, how to go from basis P to B primes, linear transformations, and so on. Some little bit of very small review of this. Okay. So now so I think before I go to, I have a little bit more to talk about tensors, because I thought since we started with tensors, let me take it at least to some ending point. So far we have restricted to Cartesian tensors, but I would also want to discuss a little bit about non-Cartesian tensors, because that will then tell you what is the power of tensors really, or what is the power of tensor algebra or tensor calculus. So, but before I go to that, I thought that maybe today we should pause and do a few examples and see that how tensor algebra, tensor calculus will firstly make certain things which we already know in a different language, how that becomes very compact. It provides a very compact notation as well as a very compact way of looking at things, and further how we can use this in our physical applications. So I'll do a few problems today. Fine. So the first, again, so let me put this here. So since we will also have exams, or we will have some point of time in exam, so you can imagine that what will be the questions. I mean, I can just tell you that what kind of questions. So I could give you some object and ask you to check whether that transforms like a tensor or not. In which case, what you need to do is take the definition and check it out. Then I could also ask you to use these ideas of tensor algebra, that means addition of tensors, or to find some resultant tensors using given two tensors by any of these operations. Then to find out or to use concepts of such things like isotropic tensors in some particular situations, and then also how to deal with tensor fields, tensor calculus, and the utilization of this. So right now, let's first take some simple problems. The first thing we will do is, let me put this. So this is our usual. So we have our usual three-dimensional space. And let's just take the origin. And so this is the position vector. And with respect to this choice of basis, this can be written as I have x1, x2, x3. These are the coordinates or the components of this position vector along the y-axis, z-axis. Now, given the position vector, if I consider this object, xi, xj, how will this transform? Okay, how does the position vector transform under rotations, or what kind of an object is this as a Cartesian tensor? So what kind of an object is this? I mean, is it a tensor? I can't hear anybody.
This quantity xi, xj.
No, I'm talking of the position vector itself. What kind of an object is it as a tensor? I mean, it's a tensor of, what kind of a tensor is it?
Tensor of rank 1.
Yeah, it's a tensor of rank 1. Okay. And then what about this object now, xi, xj? How will this transform, or what kind of an object is this? Note that xi's are the components of the position vector. Huh? Xi, xj will transform like a scalar. See, I goes from 1 to 3. J also goes from 1 to 3. So firstly, how many components has this object got?
6.
Huh? How 6?
Oh, sorry, 9.
It has 9 components. So can this be firstly a scalar at all? I have now an object which is having 9 components. So can this be at all a scalar?
Tensor.
Firstly, it is an object which has, so if I define now Tij to be equal to this, it has something which has 9 components. And you can see that this is really like as if I have taken the outer product of two tensors of rank 1. Correct? So if I take the outer product of two tensors of rank 1, what should I get? A tensor of rank 2. So therefore, this is going to transform like a tensor of rank 2. Okay, so what I would suggest to you is that please verify or please show this explicitly. Okay. So how will you show this? So what you have to show is that T prime ij should be equal to Rik Rjl Tkl. This is what you must show, okay? To prove that. So first of all, you can say that it has 9 components. So you know that a tensor of rank 2 must have 9 components. So that part is satisfied. The next part you have to show is that the transformation properties must satisfy like this. So if the 9 components transform like this, then your Tij is the tensor of rank. So how to demonstrate that now? So now take the definition. So by definition, it is this with respect to the basis B or with this basis. Now in the new basis, again by definition. So this is the way you should proceed to doing the calculations or to. So if I want to demonstrate, so this is by definition now in the new basis, it's going to be x prime I, x prime j. Because this is how I've defined this object, that's all. So with respect to this xyz basis, this is this. Now the position vector with respect to the basis b prime will be x1 prime, x2 prime, x3 prime. So in that basis, it's simply going to be this. But then I know that this is a vector. So x prime I should be equal to Rij. And I can't use j here now because this, so I will use Rik xk because this is a tensor of rank 1. So xi prime is related to xk in this fashion. Similarly, this is related to, can be written as Rjl xl. And then this is equal to Rik Rjl xk xl. But what is xk xl? By definition, this is nothing but Rik Rjl Tk. Okay. Or in other words, therefore, what we have shown is that T prime Ij equal to Rik Rjl Tkl. So I have showed this. Okay. Therefore, it is therefore this implies that Tij is the tensor of. Okay, this is the way you must use, or if I ask you to show explicitly, then this is the way, or this is a procedure you must use. Take the definition of the object. First of all, satisfy yourself that that definition. So if it's a tensor of rank m, so first satisfy yourself that that particular definition leads to 3 to the power of n components, and then find out what are its transformation properties. Fine. All right. So this quantity transforms as a tensor of rank 2. Or, I mean, trivially, it would have been simply that I've taken the outer product of 2 tensors of rank 1. So 2 tensors of rank 1, if I take the outer product, it should transform like a tensor of rank. Now let me ask you about this particular object. Suppose I give you this. How does this transform? Or firstly, what kind of an object is this? Aij equal to r square or delta ij. Where delta ij is our isotropic tensor and r square is by definition x1 square plus x2 square plus x3 square. All right, first let's forget about this. Let's take delta ij. How does this transform? Delta ij. What kind of an object is delta ij?
A rank 2 tensor.
It's a rank 2 tensor. Okay. Now I multiplied this with r square. So what kind of an object is this? Where r square is this?
It is still a rank 2 tensor.
It is still a rank 2 tensor. Why?
because r squared is a scalar.
So
Okay,
r
that's-
square equal to this, and you can see that this is equal to x1 prime square plus x2 prime square plus x3 prime square, because you know that under rotation transformation, the length of a vector remains the same, which is nothing but r prime square. Okay. So your rotation transformation preserves the length of a vector. So r square will be the same as the r prime square, and r prime square is this. So that means r square is a scalar. Now I multiplied a scalar with delta ij. So therefore, this is going to still be a second rank tensor. Now if I tell you, I construct this object. How will this transform? Or what kind of an object is this object?
a rank 2 tensor.
Why would you say that?
So r squared delta ij is separately a rank 2 tensor,
Yes.
and xi xj is another rank 2 tensor, and it is just difference between two rank 2 tensors.
Okay.
So there will be difference between each components.
Yes, very good. So you can see that this has 9 components, this object, whatever it is. And since it is made actually nothing but the difference between two rank 2 tensors, so therefore you can see that this resultant object transforms as a rank 2 tensor. So Bij, if I define it like this, it transforms like a rank 2 tensor. So therefore what we will see, I mean, we have more to deal with this later. So you can see that if I start with some tensors, I started here with vectors and or at rank 1 tensors, then I constructed rank 2 tensors from that, like here, and another rank 2 tensor with this r squared here, a scalar times our isotropic tensor, and then I got this. Now, is this object isotropic? See, delta ij is isotropic. What can you say about the isotropic properties of this? Aij? Is it an isotropic tensor or not?
Yes.
It is an isotropic tensor because you can see delta ij we know is isotropic and r square is a scalar. So obviously this is an isotropic tensor. But what about this object? Is this isotropic?
No.
So Bij is not isotropic. See, although it has a part which is isotropic, the r square delta ij part is isotropic. That is true, but then this xi xj is there. So you can see that it is not the resultant tensor which we got by taking the difference is not an isotropic tensor. Okay, so that is something which you should keep in mind. All right. So this particular example was for you to demonstrate for you that how I can start with tensors of lower rank, construct other tensors. And in this particular case, I've taken differences of some tensors and shown you that we can show that as appearance of tensor. Now, another example I want to do, where we will see that how using this epsilon ij's or the Levi-Civita tensor, our vector calculus becomes very simple. See, already I've shown you last time that if I have A cross B, suppose I have two vectors. So let's say that A and B are two tensors of rank 1. Then the cross product A cross B, we saw that I can write that as. So the cross product of two vectors, you know, is a vector. So this is going to have 3 components. We know this normally also. And the ith component of this can be written as epsilon ijk AT. Okay. I showed this already to you last time. I think I explicitly showed you the x component, y component, and z component. So for example, if I equal to 1, then I'll get 1 here. Then the only things which I can have for G and K are either 2, 3 or 3, 2. If I take 2, 3, then I get epsilon 1, 2, 3, then A2, B3, And if I take 3, 2, I'll get A3, B2, but then 1, 3, 2 will have minus sign. So I'll get A2, B3 minus of A3, B2, or that's like AY with BZ, AY, BZ minus AZ, BY. And that is nothing but the x component of the cross product of two vectors. Okay, so this gives you a very neat and nice way of writing this. Now, if I, in particular, if I apply this to, so now let me say that I have a vector field, say A of R. Okay, so this is a vector field. Be a tensor field of rank 1. Which we earlier used to call it simply as a vector field. Okay. Now, del cross A of R. All of you know how to take this. So this is exactly like this, and I use this compact way of writing this. So I can write the ith component of this object in this way as epsilon I J K del by del xj A J. Okay. So compactly I can write the cross del cross A in this fashion. So again, it's very straightforward. You can see that if I take del cross A x component, then this is nothing but del by del y of, or I'll write it in terms of x2, az of r minus of del by del x1, so E3 is right, x1 of x3, E2. So this is y first component. So if I think of the first component as the x component, what this means is del cross A, the x component is del by del y of az of r minus del by del z of a y of r. And this is what we know. Now, if I want this particular thing, so you can see how this tensor vector calculus gets simplified. Now consider del cross of del cross. Right? So now you can see that here I'm taking the cross product of this object, which is again a vector or a tensor field of rank 1, which you can demonstrate. So I'll give this as a tutorial sheet that time you can see. This is a tensor field of rank 1. Then I'm taking del cross of another vector field. So by definition now, if I take this, what will be the ith component of this whole object? See, I've taken del cross A, that gives me a vector field. Okay, again, because this is again going to give me a tensor field of rank 1. It has 3 components. Now I'm taking the cross product of that, of del with that particular vector field. And I'm asking you now, what is the ith component of this? Now, using this epsilon, can you tell me what should be the ith component of this? Think of this as some b. Okay, think of this as some b of r. So, can you tell me what it should be? Use this definition, for example. Okay, let me again ask you this. So forget this for a minute. Okay, suppose I write this as del cross of B of R, and I ask you what is the ith component. Can you tell me what is this?
Epsilon ijk dabba by dabba xj into epsilon klm dabba dabba xl.
So this is going to be pk of R, right? By definition, that I'm just use this instead of A, put this as B. Fine. Now for B, you write this as. So now your B is del cross R or del cross A of R. Okay. and I want the I. So you have to take now del cross A R, the kth component of this. Agreed? See, because this is like del cross something here, that something we have put here is this. So if I just take the kth component. But what is the kth component of this object? If I use that epsilon notations, I mean, if I use the Levi-Civita symbol. The kth component of del cross A, so instead of I must have k here. So I will have k here, then I have these repeated summations. So I use k here, then I can use L M. So then I can say del by del XL and AM of R. Agreed? So I can write this as epsilon KLM del by del XL and AM of R. Is this clear? So now what I can do is, see now after all this epsilon KLM is something which doesn't depend at all on the coordinates. So I can take this outside of this del of del by del xj. So I can write this as equal to epsilon ijk epsilon KLM del by del xj del by del xl and I have AM of R. Okay. So I've just taken this outside of the derivative part because that's anyway constant. I mean, if I think of it as a number, it's a constant. Now, what is epsilon ijk times epsilon KLM?
Epsilon IJLM.
Epsilon ijk times epsilon KLM. Here I'm doing a repeated summation of k. What is it?
Delta IL, delta JM minus delta IM, delta JL.
Okay, very good. So it's going to be del. So this I've written last time also. So I with L and J with M. K is being summed over, so I will not get anything there. So this minus of delta IM, delta JL. This is an identity I gave you yesterday, or in fact 2 days ago also. And also yesterday I demonstrated. Then I will get del by del xj, del by xl, AM of R. Fine. Now from here you can see that this tells me that if you look at the left hand side, I am taking the ith component. So my only free index is I. And you can see that that is fine here because I have I, L, J, M. J is getting summed over with this J here. The M is getting summed over with this. And the L is getting summed over with this. Okay. Now, since it is telling me that it is this expression, so if I look at the first expression, it's delta IL, delta JM times this whole thing. Now, because of the delta IL, it tells me that the answer will be 0 unless L equal to I. So, wherever L comes, replace that with I. This delta will tell me the answer is 0 unless M equal to J. So, from the first term, what I'm going to get is, I'll write this as delta. Okay, and let me write it and then I will write it. So I will get del by del xj, del by del xi, ag of r. Okay. That is from the first term. Again, you can see the summation is over j, so the only free index is del by I, del by del xi from this one. Now from the second one, what I'm going to get is that this expression will be 0 unless m equal to I and L equal to J. So this will therefore give me minus del by del xj, del by del xj, AI of R. Or in other words, what I will find is that, so if I, and then I can use the fact that I can permute these two because whether I do first the derivative with respect to x or whether I do it first the derivative with respect to y, it doesn't matter because these are Cartesian systems. So I can then write therefore my del cross AR, the ith component of this object as equal to del by del xi of del by del xg of Aj of r. So this is the ith component, okay? Minus of, what is del by, okay, so let's write it. I'll write it first and then we'll see. Okay, I can write this in this fashion. And again, it's all perfectly nice because you can see that the j index is getting sub, or the j subscript is getting summed over. I have repeated j indices here, and the only three indexes I, which is what I should get. But what is del by del xg of Aj of r? So I have now del by del xg of Aj of r. What is this? By definition, what will this be? What does it mean? Or let me put it like that. So what is the meaning of this expression? Del by del xg of Aj of r.
Del dot J.
Del dot? Yeah, tell me. You are saying something.
Del dot A.
Yeah, exactly. Because see, this is by definition nothing but del by del x1 of A1 of r plus del by del. I'm writing this explicitly because I know students have problems with this. So since I thought that at least once one should see it explicitly. But this is nothing but your divergence of A. So therefore you can see that this term which is inside this round brackets is nothing but del dot A of r. Fine. What about this quantity? When I have del by del xg times del by del xg, what does this mean? If I expand it simply without doing any meaningful thing, I mean without planning for an interpretation, just like I expanded this, what will this be? J will take values.
Del square operator.
This is nothing but your del square operator. Very good. Because this is nothing but del by del x1, del square by del x1 square plus del square by del x2 square plus del square by del x3 square. And this is nothing but your del dot del. Okay. So therefore what you will find here is that this part is nothing but minus del dot del of Ai of r. Okay. Or in other words, what we have shown therefore is that so I get that the ith component is nothing but, sorry, I'll write this first and then I'll say del by del xi of del dot A of r minus of del square. So if I write this del dot del as del square of Ai of r. Okay. And this now I can therefore write it as, if I write this now in the usual fashion without putting a component form. So this tells me that this is gradient, because now I can say it's gradient of del dot A of r minus of del square A. Okay. And this is something which you people know from vector calculus. But you can see that these kind of identities, how simple it becomes. See, okay, I mean, I took a long time to, or we did it very elaborately, but once you get some practice and experience with this, you will find that you can do this in 2 minutes or say even 1 minute. So this identity which you have, or this kind of simplifications, it really becomes very, I mean, you can do it very quickly using this tensor ideas. Okay, there are more such identities which you can very quickly evaluate using this tensor identities that give them to you. So I just wanted to demonstrate for you that the tensor algebra, tensor calculus also allows you to simplify expressions and evaluate expressions in a very neat and compact manner. Okay, so that's so much for notations and other kind of things. Now let me take another example. So now let's take this particular example. All right. So maybe I'll start with this example now. So for example, I told you that if I have conductors, let's say I have some electrical conductor. And we are only considering in the linear regime. So by Ohm's law, one can show that, so this is essentially Ohm's law, so that the current density which flows through your material is related to the electric field which is applied. So this is your electric field. So this E is the electric field. Most generally, this is going to be like this. So this is the electric field. And J is the current density. And here your sigma ij is what is known as the conductivity density. So what this means is, if I look at this now, what exactly does this mean? This means explicitly it means that your J1 of R will be equal to sigma 1 E1 of R plus sigma 1 E2 of R plus sigma 1 E3 of R. So the conductivity along the, so if you think about this, so if this is my XY thing, so if I've got this material, so this is my conductor, and if I ask what is the conductivity in this, the electrical conductivity of this material along the X direction, given that I have applied an electric field E of R, so there is an applied electric field which has components Ex, Ey, Ez along X, Y, Z directions, and if I ask you now what is the current flow along the X direction in this conductor, then you can see that it will depend upon the components of this electric field along the XYZ direction. That means it is E1, E2, E3. And these coefficients, sigma 1, sigma 1, sigma 1, which are called the conductivity coefficients. Conductivity is nothing but the inverse of resistance. If it is large, if sigmas are large, then it will tell you that you have good conductivity. If sigmas are small, you have a bad conductivity. So the first thing you can understand is it's not just depending upon the electric field along the X direction. It also can, so even if I apply an electric field along the Y direction, I can get an current along the X direction if you have this sigma 1 coefficient. This is not sigma. So, and then of course you can do this for all the others. So I've just suppose let Y equal to 1. So if I look at sigma ij, then this is sigma 1, sigma 1, 2. Now suppose I tell you that this conductor is an isotropic conductor. So I tell you that this material is an isotropic material. As far as electrical conductivity is concerned, it's isotropic. Then what will you say is the form of sigma ij? Can I write down the form of sigma ij? If I tell you that my electrical conductor, that particular conductor is a isotropic conductor. When I say it's an isotropic conductor, what does one mean by that?
J is same in all directions.
J is same in all directions. Okay. Yes. Then in that case, what can you say about the sigma, the conductivity tensor? Can I write down the form of sigma ij in that case? See, sigma ij is
Symmetric.
symmetric, but I'm saying something more. I'm saying it's isotropic. See, this is saying J1R is this. Now J2R will be, for example, I'm just writing this, sigma 2, 1, E2 of R plus sigma 2, 2, E2 of R plus sigma 2, 3, E3 of R. Alright? And similarly. But if I tell you it's isotropic, see, what do you understand by the word isotropic? See, again, go back to this thing. This is telling me that the current density across in my conductor depends upon my applied electric field. Okay. Now, I'm telling you that I have an isotropic conductor. Okay, so before you finish your conductor, forget about that. Isotropy, when I use the word isotropy, what do you understand by that?
The system is direction independent.
Or in other words, what you expect is that the current should be independent or should be the same. Somebody has already said that the current density must be the same irrespective of the direction in which I've applied the electric field. See, because from here you can see that the answers can be different depending upon the electric field I have used. If I put an electric field along the x component, or sorry, along the x direction, then I'll get sigma 1, 1, E1. This is 0. And this should be. On the other hand, Jy will give me sigma 2, 1, E1. Correct? See, so look at this, okay? So let me write down all this. Let's write down everything.
Off-diagonal elements of
Columns are same.
tensor.
One second. Just 1 minute. All right. Now, if I tell you that, let us say that I put my electric field. Suppose okay, let E be equal to E. So it's only along the x direction. And for simplicity, I've also taken it to be a constant. Right? In that case, what will happen according to this equation? Then this means that your J1 should be equal to sigma 1, 1, E1. J2 will be equal to sigma 2, 1, E1. And J3 should be equal to sigma 3, 1, E1. All right. That's what this tells me.
Columns are same.
Pardon? No, if I say that my J, all right, I think maybe I should. Okay, maybe I should say that this way. If it's an isotropic conductor, what I would expect is that if I apply along the electric, okay, if I apply the electric field along this direction, then I expect that the current should be only along this direction. Or in other words, okay. What I would expect is that this should be 0 and that this should be 0, okay, for an isotropic conductor. Because I'm applying or in other words, what I expect is that okay, let me put it in this fashion, that I expect that the current should be parallel to the electric field, the direction of the applied electric field. Because that's what I mean. See, why do I call that as isotropic? Because if I apply the electric field,
Sigma will be diagonal.
so if I apply the electric field like this, then my electric current should be across this. If I apply it in some other arbitrary direction, E, then again my current should be parallel to this. Because if the current is not parallel to this, then it means that I have some components which are not along the E itself. Okay. So when I say it's an isotropic conductor, what it means is that my current should be parallel to the electric field. Okay. So maybe I'll write it like that. But so if your current is parallel to the electric field, to the applied electric field. See, because then it tells me that irrespective of which direction I put my current, my electrical conductivity is the same. Because, irrespective of which direction I put my applied field. So whether I put my electric field like this or like this or like this, any direction, my current is still going to be parallel to that. So it means that my current or my conductivity does not depend upon the direction in which I've applied my electric field. So that's why I call that as an isotropic conductor. Isotropy means that it doesn't depend upon the direction. It's or rotationally symmetric. That's what it means. Okay. And that therefore isotropic conductor means that your current must be parallel to the applied field. And it's independent of which direction you are putting the applied field. So in that case, what should be the form of my sigma ij?
Diagonal.
Okay, so in that case, if it's diagonal, what should be? So right now it's a second, because this is an object with 9 components, and if it has to be diagonal, then how should I write the sigma ij as? Using whatever we know earlier.
Some scalar
Delta
type
ij.
delta ij.
So I can simply write this as some lambda times delta. So for an isotropic conductor, I will get sigma ij equal to lambda times delta ij. Then this implies from there that ki of r, or let me just put it as ki, will be equal to lambda times delta ej, which is nothing but lambda times j, okay, or j equal to lambda times. And this is exactly what you people have been studying. The elementary schools or elementary BSc level perhaps. This is how you learn about Ohm's law. That J is simply proportional to the applied field. And you simply have lambda, where lambda is simply a scale. See, but once I tell you it's isotropic, actually once I use the word isotropic, then I know that this must be an object which is a second rank tensor. That is, why should I expect that this should be a second rank tensor? Okay, I'll do that by using the quotient law later. Here I have got something which is a vector because my current density will transform like a vector. This electric field, again, we know that this is a vector field. So the left hand side and right hand side are both vector fields. Then by the quotient law, one can show that this object, if I get such a relation in any frame, then in that case, whatever is this object, which must have 9 elements here, must transform like a second rank tensor. Okay, I will establish this later on. So right now assume that once I have such a relation, then this, whatever is this object, must transform like a second rank tensor. And in particular now, if you find that you have an isotropic conductor, this is a second rank tensor. The most general second rank isotropic tensor which I can get is simply this. So I can use whatever we have learned earlier and say that I know that the only second rank tensor which is isotropic is delta ij. Most generally I can multiply with some arbitrary scalar. So I get this. So my conductivity or my current electric field relation must be of this form. Okay. And as I said that to establish that this is a second rank tensor, I will use the quotient law, but I'll do that later. So just accept that law. Okay, now I don't have an isotropic conductor. So this is true for an isotropic conductor. Now assume that you have an anisotropic conductor. So if I have an anisotropic conductor, more generally I will have this sigma. This is my conductivity tensor. So what this tells me is that the current flow along different directions depends upon the electric field in which you have applied, and it also will depend upon the material properties or these coefficients, these conductivity coefficients, and which actually are the properties of the material which will depend upon the crystal structure. So typically for any conductor, it will depend upon the crystal structure, it will depend upon what kind of atoms are there, and so the electronic configuration of course. So experimentally you can measure. Now let us assume that I give you somebody has done an experiment on some conductor and they've given you this particular tensor. So it's like, you have got a material. So essentially you can measure the resistance. So from the resistance you can get this or vice versa. So somebody has done these experiments and we have got the conductivity tensor of this form. So let us say that I got this. Fine. Sorry, this should be that. Okay, now you can also see that okay. I say, let me say that I have this. Now what you do is show that there is one particular direction. So I'm going to ask you the following. So I've given you this. Now my question to you is that, or I'm going to state to you that, show that there is one particular direction. So this is, obviously when I've done this, it's with respect to some particular choice of coordinate axis. So people have taken your material, chosen a certain coordinate axis and done the measurements. So let's write it properly. So I have taken my material, chosen some particular set of axes for the coordinates. So the XYZ axes are chosen in some particular fashion. And with respect to those axes, I've applied the electric fields, and then I've got this sigma or the conductivity coefficient tensor in this fashion. Okay. Now I'm going to ask you, or I'm going to tell you that find that or show that there is one particular direction, that there is some direction along which there is no current flow. How will you find it? Show that there is at least one direction along which, when I say direction, it means not just this XYZ, but that there is a particular direction along which, if you apply the electric field, then there is no current. So to do that, I will show you how to do this. So let us do one thing. Now this is a vector, this is a tensor equation. Because I have Ji equal to sigma ij Ej. Fine. Now this particular equation, or when we've written this, I've written this with respect to this particular choice of basis, where I've chosen the coordinate axis as I cap, J cap, and K cap. Now suppose instead of this basis or these kind of basis vectors, I cap, J cap, K cap, let me say that I've gone to some other basis vectors, say I cap prime, J cap prime, and K cap prime. Okay. So I choose another set of three orthogonal basis vectors where these are related to this by some rotation transformation. Now, according to this equation, because this is a tensor equation, I can write down in that new basis, I can simply write down Ji prime should be equal to sigma. See, this is where I could directly write this, because the left-hand side transforms properly like a tensor of rank 1. The right-hand side also transforms like a tensor of rank 1, because I'm combining a tensor of rank 2 with that of a rank 1 tensor. I'm contracting these two. So therefore, I'm going to get a tensor of rank 1. So I can simply write down this equation in this form in the new basis. So with respect to the new basis, this equation will simply become like this. Okay, and this way, we implicitly have done this in our usual physics. That, for example, when I have F equal to AB, this is our Newton's law. This is left-hand side is a force which is transforming like a vector. The right-hand side, I have this M which transforms like a scalar multiplied with an acceleration which transforms like a vector. So right hand side transforms like a vector, the left hand side transforms like a vector, right hand side also transforms like a vector. And if I go to any other coordinate system, the equation will simply become like this. Okay. So that's why it is independent of really a choice of coordinate system, because the form of this equation remains the same. On the other hand, if you had some arbitrary kind of objects here, so if I had a scalar on the left side, and if I had a vector on this side, then this really is not a very good way of writing an equation. Firstly, it doesn't make sense. And you can see that the form does not, or the form is not preserved under different choice of basis or different choice of coordinate axis. So this, by the way, that where the form is preserved, so even the coefficients are being preserved. So if I have a particular equation, a physical equation, and the form is being preserved under coordinate transformations, in this case, for now, let's only restrict to rotation transformations, then that's called a covariant way of writing my equation. Or this is, you will say that this equation is covariant. Covariant also comes in another way, another definition. I will also deal with that a little later. But when we write it like this, that the form of an equation gets preserved under coordinate or here rotation transformations, we will say that this equation is covariant under rotations, for example. Okay. So similarly here, when I have such a tensor equation, the form gets preserved, so I can simply write down the new basis equation like this. But what is this equation? How is this related to this? Can simply relate this to this in the form that I will get an Rij. So this J prime I will be Rij, Jj, Rik, Jk, and then I use the transformation properties and figure that out. Okay. So let's write this down. Or let me write it like this for a minute. Now what I want to ask, I've given you this, so let's say this. So in the new basis which I've chosen, the equation simply becomes this. And now what I'm asking you is, or I'm asking you to show that there is a particular direction or some particular I prime, G prime, K prime, one of these. So the best way is what you can do is you transform to show that what you can do is transform this now to a basis in which the sigma becomes diagonal. Okay. So first of all, transform this to a basis in which the sigma becomes diagonal. So because if the sigma becomes diagonal in that basis, then in that case you will simply find that J1 prime will be sigma 1 prime E1 prime, J2 prime will be sigma 2 prime E2 prime, and J3 prime will be sigma 3 prime E3. And then show that in that basis, one of those diagonal values becomes C. Right? So first of all, let us find a basis in which this. So before we show that the current flow along a particular direction is 0, let's first find out the diagonal basis. So let's find out a transformation which will diagonalize this matrix. So how do I do that? I want to diagonalize my matrix, sigma. How does one do that? This is what you've learned in your MNP 1 last semester. This is what you've learned, not last semester, the first semester. Matrix algebra, how do you find out? How do you diagonalize your matrix? How do people diagonalize? I'm sure every one of you did this problem, right? That now forget about this problem for a minute. You just think of this as a matrix. And I want to diagonalize this basis. Diagonalize this matrix. So how do you diagonalize the matrix? I mean, what is the procedure which you learn? Matrix algebra, all of you are familiar with it. What is the procedure which you people have used?
Similarity transformation.
Pardon?
Uh,
A similarity transformation, that is correct. But typically, I mean,
Find the eigenvalues and eigenvectors of this.
so the easiest thing is that you just, the diagonalization problem, essentially what you do is you use corresponding eigenvalue problem. So here I have sigma. So find out this. So given a matrix M, okay? Suppose you have a matrix M and I want to diagonalize. It's correct. What you said is correct. I want to do the similarity transformation, but to find out the similarity transformation, what you do is solve the corresponding eigenvalue problem. So you solve the eigenvalue problem. That means what you have to do? Find the eigenvalues, lambdas.
Ma'am,
Yes.
ma'am, the determinant of the matrix is 0. So we can directly conclude that one of the eigenvalues is 0.
Yeah, that is
So
correct.
that would prove the point that there will be at least one direction along which
That is correct. So now I want you to find out exactly what is that direction. That is correct. What you said is perfectly correct. That the determinant of this sigma is 0. So it immediately tells you that one of the eigenvalues must be 0. But then now I want you to find out what is the direction along which the current flow is 0. So how will you do that? Without solving the diagonal problem. Suppose you, since you already demonstrated that there must be at least one eigenvalue where lambda, which should be 0. So if I want to find out now explicitly what is the direction along which the current flow is 0, then
find the eigenvector corresponding to eigenvalue 0.
exactly. So in fact, what you can do is, so basically what you do is when I want to diagonalize a matrix M, what you do is solve the corresponding eigenvalue problem or solve this equation. So here what you do is find out the eigenvalues lambda and the corresponding eigenvectors IU. Okay. So in this case, what you can actually do is very simply, because you can see that the determinant is 0. Now I can use that particular knowledge and simply say that I will find out the U for which mu equal to 0 identity. Because I know that lambda must be 0. So lambda 0 into U. And that I can see from the determinant. We know that the determinant does not change under any kind of a similarity transformation. Right? So I can directly do this. And now my M is, in this case, my M is nothing but sigma ij. So I simply will take this 1, root 2, 0, root 2, 3, 1, 0, 1, 1 times U1, U2, U3 equal to 0, 0, 0. Solve for lambda equal to 0. Right? So this will then tell me that I have U1 plus root 2, U2 should be 0. Then I get root 2 U1 plus 3 times U2 plus U3 should be equal to 0. Then I'll get U2 plus U3 should be equal to 0. Now solve this set of simultaneous linear equations. And from there, okay, we can solve it actually here, for example. So let me solve this. So from here you can see that this tells me that U2 should be equal to, or root 2 U2 should be equal to minus 1. Let's go. And from here I guess that U3 should be equal to minus 2. And then from here you can see that this probably will be redundant because I will get root 2 times U1. So let's just see this. 2 times U2 2. Okay, so this tells me this from here. Right? 3 times root 2 plus root 3. So this gives me therefore that root 2 u1 plus 2 times root 2 equal to 0. So this is exactly the same as this. Okay? Because if I just divide by 2 root 2, then I'm going to get. Okay, so this is root 2 and 2. So which implies that u1 plus root 2 equal to, which is this equation. So this equation I don't need to worry about. So I just have these two. So I have this relation that I have u1, then I have minus 1 by root 2 u1. So my eigenvector u is this term. So the eigenvector corresponding to lambda equal to 0 will be is given by, so from here I have just u equal to minus 1 and u equal to minus 1. So I will get u1, then I will get minus 1 by root 2 u1, and from here I will get minus of u2, so that is a u2 plus 1 by 2. Agreed? So my u equal to this. Okay, then I can choose some arbitrary u1. There's no point in making it the 0 vector because that's not what you're interested. So I just put 1 here. Then what you can also do is normalize it if you like. But this particular one, so if I take the unit vector along this u cap, so u cap if I define as u by normal, the length of u, then in that case what you will find is that this is the direction along which, so if I take u cap, which is a normalized vector corresponding to u, which is given by this 1 minus 1 by root 2 plus 1 by root 2. So you can think of this as, so it's like 1 by root 2 and minus 1 by root 2. So it's here and somewhere. So somewhere here. So it's like something like this. So along this direction, there is no current flow. Or in other words, what it means is that if I apply my, 1 second, no, there is something, why is it saying? It's not plugged in. Just 1 second, please. There is some problem with mine. No problem. Just Just 1 second, I'm just coming back. So, see that.